What's crack-a-lackin'? Pre-calc. This is Mr. Taryn rocking with you again here. Today we're going to look at 1.4 day 2 box problems. And these can be really difficult. I'm going to go through all three examples from this PowerPoint. So this video will be pretty long. Go ahead and if you're going to watch, if you want to skip to different examples, just kind of go through the video however you need to. But let's do it. We're going to skip through all this. These are just basically your perimeter area, surface area, and volume formulas. You should know those, have those written down somewhere else before you do these questions. Just the general procedure here is, first thing you always want to do with a box problem is draw a picture. Then you kind of write down what formulas you're going to use, and then you're going to end up substituting stuff, most likely. And then eventually, you're going to have to graph something on your calculator and find either a maximum or minimum point, because that's what we're doing here. These are optimization problems, okay? So let's just get started here. I am going to take this and make it much smaller so I have lots of room to work. So here we go. So I know you can't read it, but it's the notes are online, but here's my first example. I have a square with side length x are cut from the corners of a rectangular piece of sheet metal with the dimensions of 6 and 10 inches. The metal is then folded to make an open-topped box. That's important. What is the maximum volume of the box? So I'm trying to maximize volume. So I'm going to draw myself a quick little sketch here. Here is my sheet metal, and it said that it has squares cut out of the corners. And I don't know what the length of those squares are, so I'm just going to say x. This is a length of x here, length of x here, length of x here, length of x here, right? Because it's a square. So this is also length of x, this is a length of x, and this is a length of x, 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 x. So there's my picture. That's my sheet metal that I'm eventually going to kind of fold together to make an open-topped box, or kind of like a tray if you want to think about it. So I need to somehow relate perimeter, because it's giving me the perimeter, and volume. So I need to do that somehow. Volume is what I'm maximizing. Volume is simply length times width times height. But I'm going to have to do some sort of substituting to figure this out. So it said that the metal is 6 by 10. So I know that this whole length is 6. Is 6. And I know that this whole length is 10. However, remember we cut out these little squares on each corner here. So really, if you think about the perimeter here, or you don't even have to think about the perimeter. If you think about these side lengths here, then this side right here would just be 6 minus 2x, because we're cutting out this x here and this x here. This side right here would be 10 minus 2x. Okay? So now we got to start thinking about how we're going to do this as far as volume. So I can say this is my length right here, this is my width, and then we'll figure out my height. But if my volume formula is length times width times height, my length here is 10 minus 2x. My width here is 6 minus 2x. And if we're going to fold the corners up, the height of my actual tray would just be x, because that's what's being folded up. All I have to do here now is I just can take this function. If you want to multiply everything together, you can. That's a waste of time, though, because you can literally plug this right in to your calculator, go into your y equals, and plug this equation in, and then graph it. Once you graph it, you will get some sort of a picture. And since we're trying to find the maximum volume, what you're going to want to do is, if your curve looks something like this, you're going to want to do your second trace maximum to find that value. So go ahead and enter this into your y equals, do your second trace maximum on the top, and then your x coordinate should be 1.21, and your y coordinate should be 32.835. Okay, and you got to ask yourself, well, what do these numbers mean? Well, remember, this is your x value and this is your y value. Your x value in this case is just how much we're cutting out of each corner. Your y value is your function for volume. So that 32.835 is going to be your maximum volume. Now let's go back and look what the question asks. The question asks, what are the dimensions of the box that give the maximum volume? So it's not even asking for maximum volume. It's asking for the dimensions of the box. So I'm just going to simply plug in for x here. I'm going to go 6 minus 2 times, we said 1.21. That's going to be the width. And that's going to equal, I believe it's going to be about 3.58, or we'll just say 3.6 inches. We're going to find length next here, which is we said over here. So that's 10 minus 2 times 1.21, which is the value of our x. I'm going to do it in my calculator real quickly. I'm getting an answer of about 7.6 inches. And then our height, so that was our width, our length is right here. So our height, remember, was just the value of this x, because that's how much is being folded up, which is just 1.21. So that's how you do the first question. That one's not too bad. Let's keep moving forward. So in this question, we have a rectangular pen. It's being constructed using a building as one side and 60 feet of fencing for the other 3 sides. Find the dimensions that will give the greatest area. So I want to find maximum area. So again, the first step here is kind of just draw a picture here. So that's what we're going to do here. So let's do this. So here is the building. Okay, and here is the pen. It's going to be on the edge of the building, right? So it's got to look something like this. Let's do it in a different color. Right, so that's what it looks like. So I got to figure out here, I'm trying to find the maximum area here. So I know area is going to be length times width. I'll just call this length, this width, and then we got to start filling these in. It says, though, that we only have 60 feet of fencing total for all 3 sides. So I can say, in this case, perimeter is equal to 2W plus L, right? Because we're only fencing in 3 sides. And I know that that perimeter has to be 60 feet. So what I'm going to do here is I'm going to move some stuff around in this equation so that I get it down to one variable. It doesn't matter which one you solve for. I'm just going to solve for L. So what I'm going to do here is I'm going to subtract 2W from this side, and I get L is equal to 60 minus 2W. The reason we're doing that is now I can go ahead and substitute that in for L, and then I will have only W as my variable. So that would look something like that. Area equals, we're going to substitute for L, we're going to substitute that 60 minus 2W, and then times W. And this is what you can go ahead and enter into your graphing calculator. Again, we're finding a maximum here, so when you graph that, your graph should look something more or less like that. And we're finding maximum. So this point, wherever that is on your graphing calculator, is what you want to find. So when you do second trace maximum, you should get the coordinates 15, 450. Remember the x value, right? Or our x value is really, in this equation, is really our length, our width. And our y value, if we think about it, is our max area. So let's go back and look at the question. It says, find the dimensions to give the greatest area. So yeah, 450 is our greatest area, but really we're concerned with the dimensions. So width, I know, is 15 from this right here. That was the width that gave us the maximum area. Now I can go ahead and take that and I can plug that in right here. So 60 minus 2 times 15 would give you 60 minus 30 is 30, so your length is 30. And we should probably label, so what is this? Feet. Okay, so our width is 15 feet, our length is 30 feet, and we're done with that question. All right, moving on. This is probably the hardest question on this PowerPoint, but we're going to do this the same kind of way that we've been doing the whole time. So the first step is to draw a picture. Okay, so a box is to be constructed having a square base but different height. The volume of the box is 32 cubic inches. Find the dimensions that will give us maximum or minimum surface area. Okay, so this one's involving volume and surface area. So we're going to look at those two formulas. And what I'm trying to do is I'm trying to minimize whatever my surface area formula is. Before we do that, let's draw a quick picture here. So I have a box, square base. That's really important to this example. Okay. So let's keep drawing here. So there's my box, and I know that my base is square. So that means each side is the exact same. So I'm going to put some tick marks in there. I know the volume is 32. Well, so I'm just going to start assigning some variables here. I don't know what this length is for the square, but I'm just going to call it X. Okay? And I know I'm just going to call this height from my box. And that's pretty much it, right? My length would be here, my width would be here, and my height would be here. Those are the three dimensions. So I know that volume is equal to length times width times height. I also know that the volume is 32 cubic inches, so I'm going to substitute that for volume. I know my length is simply just X. I know my width is simply just X, and I do not know my height. That is what I'm going to have to figure out here. Let's take a look at surface area here. My surface area formula for this would be 2 times the area of my base, I'm going to use capital B for that, plus 4 times my what's called lateral area. It's these little rectangular panels, and there's 4 of them, and that's really just X times H. I can say that the area of my base is just X squared because I'm multiplying this times this. So 2X squared plus 4. Oops, let's erase that. Plus 4X times H. Now the problem here is that you have 2 different variables. You have X's and you have H's. So we need to somehow get that to all be one variable. So what I'm going to do is I'm going to take a look at this equation, and what I'm going to do is I'm going to solve for H. So let's do that over here. I know that 32 is equal to basically X squared times H. I'm getting X squared from X times X. I'm just going to divide both sides by X squared, and I get H is equal to 32 over X squared. So I can then take this and substitute it right in for H. So my new formula will be surface area is equal to 2X squared plus 4 times X times 32 over X squared. Now if you want, you can, simplify the X with the square. You don't have to. What I would recommend doing is just typing this entire thing into your graphing calculator. Once you do that, you'll have something that looks more or less like this, and we want to find the minimum. So you're going to go second trace minimum, find that, and your coordinates should be 3.175, comma 60.476. This x value really is just the length and the width. Your y value is your surface area because that's the function we were putting in. And the question asks, find the dimensions of the box that will give the minimum surface area. Well, these are my length and width, so I can say length 3.175, width 3.175. We said height is equal to 32 divided by x squared, which would be 3.175 squared, which would equal, let me just do it in a calculator real quick. 32 over 3.175 squared. And I'm getting a height that's actually 3.175 about as well. So the height, the length, and the width are all the same, and your minimum surface area we saw is 60.476. So those are all the answers you're looking for. That one was a pretty difficult question. All these are. So make sure if you have any questions on anything, please reach out to your teachers. We know this is difficult. We're more than happy to help you. You just got to let us know. So with that being said, y'all take care now. Taryn out.